a table, and we use it to measure forces, hence the term a force table. Okay? Not the most clever name in the world, but it works. So what you want to do is establish a system where it's in equilibrium. Okay? So visualize this is like a three-way tug of war. Okay? We got Gershon, Colin, Anna. And it's a three-way tug of war. All right? So right now, you've got this ring. Okay? So what you want to do is adjust this so that ring is centered right in the middle. So if you look at the top of this table, it's laid out like a protractor. And we're going to use the same system. 0 is a positive x-axis. So keep one of these at 0. Okay? Don't change it. Keep one of those at 0. Then you're going to go counterclockwise, and get to like, in this case, that's like 135, and then I'm over here at 224, whatever that is. So there's two things that you can do to adjust this system. You can either change the amount of weight that's on it, okay? Like for example, I took this one off, and as soon as I did that, then the system's no longer in equilibrium because the ring is touching on that. So I'm going to put this back on, boom, now I'm at equilibrium. So you can either change the amount of weight that's hanging, or you can loosen the clamps and you can change the angle of where these things are pulling. Okay? Those are the two things that you can do. So what you want to do is establish it where it's at equilibrium. If you're not sure it is, do what I call the tap test. If you give it a little bit of a tap and it stays there, it's actually in equilibrium. If you tap it and it moves and this ring starts to hit on the post, then you're not quite at equilibrium and you need to fine tune it a little bit. So on this one, you're going to have three vectors, A, B, and C. I specifically tell you that vector A is at 0 degrees. Okay? Everybody's going to have the same vector A at 0 degrees. Now, you need the mass. So once you get in equilibrium, take all of these off, and you're just going to begin to add them up. So like this one's 20 grams, this one's 50 grams, and you're just going to keep adding them up. Now, once you get the total mass, how are you going to calculate the downward pull of gravity acting on the system? Multiply it by 9.8. Take the grams, convert it into kilograms, boom, there you go. Do not make these negative, okay? The angles are going to define the system. So just take the mass, multiply it by G, call it good, okay? Then record those values. So here's the main idea of this. This is like a three-way tug of war. So let's say Anna's pulling this way, Gershon is pulling this way, Colin's pulling this way. So this is like the quintessential example of what a free body diagram would look like. You've got force A, force B, force C. This is acting out from a common center. But here's the story. If I were to take Anna's vector, and then I'm going to take Gershon's vector, which is over here. So I've got Anna's going this way, and then I'm going to take Gershon's and draw it this way. Okay? And if I were to just draw the resultant of those two, which direction would it point? Either towards me or towards Colin. Or Preston, I'm sorry, towards Preston. My bad. Was thinking Colin and then had Colin on the break. So it would point towards, so if I were like this, if I just had these two vectors, the resultant would be pointing towards Preston. So all this vector is doing, this vector over here, all that's doing is balancing out the other two. This vector over here is balancing out those two. This vector is balancing out. So what one vector is doing is balancing out the resultant of the other two. So in terms of data, all you have to do is adjust the angles. Don't change the 0. Okay? You can adjust the weights. You can adjust the angles. Now, what I do not want 3 equal amounts of weights at 120, 240, and 0. Okay? They have to be different amounts of weights. I don't want 3, Gershon, 3 equal weights. Okay? Got it? Good, grand, back we go.